Okay, welcome back, everybody. It's time for the afternoon plenary of today. My name is Anna Rotkirk. It's my great pleasure and honor to introduce Professor RonaldLee, Ron Lee, from the University of Berkeley. We are very pleased to have him here as an EB plenary speaker, especially since he really flew here directly from the PAA, Population Association of America, meeting where he was awarded the laureate biggest honor of the IUSSP, International Union of the Study of Population. So congratulations for that distinguished merit, and thank you for transferring so quickly here. In this morning's plenary, Olivier Morin talked about traditions and attractors. If you are in the field of family sociology and demography, as I am, the references to Lee, and especially for me, Lee 2003, are a huge, very often occurring and very attractive reference to put. Especially so since there are two very famous and seminal Lee 2003 references. So now you get two for the price of one. The first is related to the demographic transition. That's a title of one very famous paper called The Demographic Transition, 3 centuries of continuing change or fundamental change. So if you're short on word count or something and you need one reference to this ongoing process of shifting to ever smaller families and ever longer lifespan, that's one, Lee 2003. The other Lee 2003, which I believe you will be somewhat speaking about today, appeared in PNAS, and it's about rethinking the evolution of aging amongst humans and also among other species. Professor Lee is also very famous for developing methods, especially related to the forecasting of mortality. There's a famous Lee and Kramer method for doing this. So it's sometimes said that demography is about 3 things: births, deaths, and statistics. And if this is so, then really Ron Lee is demography, or demography is Ron Lee. I don't know how the causality goes, but he certainly ticks all these identity boxes in that specific field. However, one reason we wanted to invite him here was because he's also very interdisciplinary. As far as I understood, you started by studying demography at Berkeley, but then the PhD was made in Harvard in the field of economics. And later, back in Berkeley, Ron Lee founded the Center for the Economic and Demographic Study of Aging, so combining these two disciplines. Also, and especially of interest for us, is that he uses life history theory, 3 words that you don't usually hear in the mouths of demographers or economics. And I would actually personally be very interested in knowing at what point of your scientific life you started to become interested in biological and life history theory. So we look forward to your talk, and welcome.
Thank you very much, Anna, for that generous introduction. And I got interested gradually. I was a little interested as a graduate student, and then I got more and more. But it was really that 2003 paper which sort of arrived as a lightning bolt for me and pulled me into the field. So it's a great pleasure and honor to be here, and thank you so much for inviting me to this wonderful meeting. So Hamilton made many contributions, but 2 were particularly relevant for my talk today. First, the theory of the evolution of altruistic behavior and kin selection, And second, a paper on how natural selection shapes senescence and the age schedules of fertility and mortality, a very important paper in life history theory. Now, intergenerational transfers represent a kind of bridge between these two topics, because the transfers are altruistic and they have an age pattern. And I want to talk about both of those, and in fact, that bridge and its relation to the evolution of sociality, partly both sort of vertical sociality in the sense of intergenerational transfers and horizontal in the sense of social sharing. The talk is based on a series of papers that are quite mathematical, but the talk won't be mathematical, and there's a list of the papers at the end of the talk and a list of other references, and I want to thank my many collaborators, Carl Bow, who helped the simulation I'm going to report, Cyrus Chu and Chen, who I worked on optimal life history theory with, and Karen Kramer and Hilly Kaplan, who were very helpful with anthropological collaborations. So, in part, I'm going to be talking about the evolution of mortality and longevity in humans, and this is just to sort of fix ideas. We have the Swedish, sort of contemporary Swedish age schedule here, and then here we have the Aceh from Hill and Hurtado, and we have Sweden in around 1750. You can see those two are quite similar. Okay, so let me start with a sort of tour of the logic of my presentation, which is to start with the thought that the usual setup for thinking about life history theory is what Jonathan Wells presented in his talk yesterday, I guess, and what Mike Irvin talked about today, and I talked about in much more sophistication and detail than I will, but namely, we think of an organism allocating resources among survival and maintenance on one hand, growth on another, and on the third hand, fertility, reproduction. Where do those resources come from? Well, for an isolated individual, those resources have to come from the individual's own efforts, and that very much limits the life history possibilities for that individual. So intergenerational transfers, in particular parental investment or grandparental investment or broader social investment, mean that the young individual has broader options and a wider range of life history possibilities is open to it. So I'll talk about that. Then the very existence of these patterns of intergenerational transfers changes the selective pressures on the shape of the demographic profiles and other aspects of the life history. And I'll talk about that. And then the parental investment in itself creates new threats to reproductive fitness. Perhaps the most severe is the threat of early parental death, and then loss of all that has been invested, perhaps over the years, as with humans. Somebody referred to this as, I think, stacked childbearing or something of that sort. I really like that term, but you lose all. If the offspring are dependent on the parent dies early. So that's one threat. The other is a kind of life cycle squeeze, a piling up of consumption requirements at a certain stage in the reproductive life cycle, and I'll talk about that also. So those problems are then resolved by broader social sharing, horizontal sharing, which I'll talk about, food sharing I'm going to focus on. And then that, in turn, creates new problems, new distortions to natural selection that changes the shape of these age profiles and other aspects of social behavior as well. So I'll talk about that using a a micro simulation in which, in a sense, you might say evolution is taking place in a simulated way in a stochastic environment. Okay, so that's a roadmap for where I will be going. And so, if we start with this isolated individual with the constrained options because it can only use the resources that it itself can gain, and at the beginning of life it is very weak and small and so on and so forth, very limited possibilities. An organism like that might, if it had the opportunity, might benefit from a loan from the bank of nature. It might be able to raise its reproductive fitness if it could borrow resources to invest then and then repay them later in its life history, conditional on its survival. Now, that would be true if the marginal fitness value of resources, say in childhood, which early life, which could be invested in armor, body growth, brain growth, development of an immune system earlier, all of these kinds of things, if the marginal fitness value of resources at the beginning of life are greater than they are in adulthood, then you gain fitness by transferring resources from adulthood to childhood. And that's essentially the story of the evolution of intergenerational transfers. Now, of course, it also depends on the interest rate, not just on this marginal value. I'll come to this in a moment. But, of course, the Bank of Nature doesn't exist, but intergenerational transfers provide somewhat the same function, actually better than a bank. This is much like the story, for example, of students having to borrow for higher education in Europe or the US these days, as opposed to receiving it as a transfer from their parents. It makes a lot of difference to their whole life history. Okay, so with the intergenerational transfer, with parental investment, new opportunities are opened up. Perhaps a slower life history is possible, later maturation, but maturation with a more powerful soma in whatever dimension, horns, teeth, claws, brain, whatever. Okay, so there are many species, however, which don't have that high rate of return to high marginal valuation of resources in early in life. And for them, intergenerational transfers wouldn't make sense, and this borrowing from this Bank of Nature wouldn't make sense. But many, many organisms, of course, do have parental care to some extent. So mammals, birds, many insects, many fish, and even some trees, I don't know about other plants, do have parental care, do provide parental care. So evolved transfers of this sort form a downward chain. I'm really talking about net direction of transfers here, net of any upwards that may occur. So one generation transfers to their kids never repay that to the parents. That would be an exchange and not a transfer. But instead, their kids, when they become adults, they carry the same genes that induced the parents to make these transfers, and so they're motivated to make the transfers themselves to their offspring and so on forever, as long as we exist. Probably net upward transfers never occur, except possibly in the case of human hunter-gatherers, where they may be tied to some aspects of the division of labor, which Chu and I explore in a 2013 paper. And of course, in industrial societies, there are massively upward transfers in some countries, particularly aging countries in Europe or Japan. That's another topic. So in a stationary population, a zero population growth rate population, if an offspring, say, receives a transfer of, say, $1,000, 1,000 calories of energy from an adult who is, say, 10 years older, 30 years older, and if the probability of surviving from the age of receiving that to the age at which it was given is, in this example, 0.5, then that same individual, on reaching the age of making that transfer, is going to have to make twice as big a transfer in order to balance the books, as it were, to allow for the fact that half of those who received the transfer didn't make it to adulthood. Low survival makes a transfer system, a transfer life history, very costly and inefficient. And so, for example, for an orchid seed, where an orchid produces maybe 1 billion seeds, there's an extremely low probability of survival. This isn't a life history strategy in which intergenerational transfers would be favored. Longer life, on the one hand, reduces the size of this payback, this downward transfer that the former offspring now makes as an adult, reduces the relative size of it. It also gives a longer period in which the organism benefits from that early investment. And so there's a co-evolution of longevity on the one hand and intergenerational transfers on the other. Carey and Judge was an early paper along these lines, and Chu and I have a paper to that effect, on a mathematical paper on the evolution of intergenerational transfers and longevity. So if we look at some data on economic life cycles for hunter-gatherer groups, this is an average of data that Hilly Kaplan presented in 1994 article, Aceh, Piro, Machagenga, Amazon Basin, and Nancy Howell's analysis of the data on the Kung Bushman. You get something like this, and there's some striking features, probably very familiar to you. But first of all, we see that here, these are the offspring. They're consuming this much, but they're producing that much. They're clearly not following that model of the life history in which they're just allocating their own resources they generate themselves. They're clearly using resources that they're getting from others, and the others are these adults, parents and grandparents and perhaps non-kin who are transferring resources downwards. These data are per capita. If they were weighted by population size, then this would be much smaller and this would be bigger, and they'd sum to zero, the pluses and the minuses. And the other striking thing here is that the elderly are continuing to produce more than they consume up to the end of the range of observation ages. This is something similar, more recent, probably better data for the Tsimane, from article by a number of people here. An old article, it's probably something more recent, but this looks very much the same, except I note that females have a much later break-even age. I think it's 28 in this case. Males, 20, about like this example. Okay, so the story is very similar. I think it's a pretty robust story. And this is some from an article that Karen Kramer and I did on not a hunter-gatherer group. This is Mayan subsistence slash and burns wooden village in Yucatan. You can see, of course, there's a lot of noise here. But basically, it looks qualitatively similar. You have the older people still continuing to produce more than they consume. But there's a shorter period of dependency here. There's an earlier break even, and the children are much less costly. I think this is differences in the production technology. hunting and gathering and this sort of agriculture in which children can work safely, and it doesn't require great skill, many of these tasks, and so the children become productive at a much earlier age and pay some of their own costs. And if we sum these things up, then focusing here for the Piro-Machigenga Aceh, it takes about 10 years of average consumption to be transferred to kids in order to get one surviving 20-year-old. Kids are extremely expensive. To produce one surviving kid in the Maya group, it only took about 3 years. The Mayan kids are much less expensive. And I should also say what I didn't, that the adults never produce much surplus in the Mayan setting, but they produce enormous surplus in the hunting and gathering setting. Unfortunately, the data used, the methods are different, and so we can't be sure these are real differences between the two groups, between systems of production and so on. Now, so here, the green is the same data we were looking at just before. That's hunters and gatherers. This is sort of for, this is a little bit off topic, but if we look at similar age profiles for developing countries, we have the red line for consumption by age, and you can see it remains high, and production by age in developing countries is like this. This would be low income and middle income countries. And you can see that unlike the hunter-gatherer groups, a big gap opens up in old age as well as in childhood. This is, unlike the subsistence agriculture, swidden agriculture, in settled agriculture, older people have property and it just changes the whole dynamic, and something like retirement or a different form of labor comes into play. And then finally we have the blue, which is rich industrial countries, and you can see how consumption rises with age and how suddenly people withdraw from the labor force under the influence of our pension systems and such. I'm going to return to that if there's time. Now, so the presence of intergenerational transfers changes the forces of natural selection. And so let me just sketch Hamilton's original story, very plausible and very influential, which is basically, mutations are occurring every time there's a birth. We think of each mutation or some of these mutations as raising mortality at a particular age. But these mutations then are constantly being removed by natural selection from the population with a different force of selection at different ages. And at ages past the age of reproduction, there's no force of selection against them, and so mutations that affect old age just accumulate and make us weak and unhealthy and so on. So the force of selection is proportional to the share of the lifetime reproduction that remains after a given age. And this share starts at 1 at birth, and then it stays flat at 1, and then at sexual maturity begins to decline throughout the reproductive years, and then hits 0 at menopause. So we would then expect these deleterious mutations to be much more present in the population past menopause or late in the reproductive years, and we expect mortality to rise catastrophically after that, and it to be low and flat prior to sexual maturity, something like this. Okay, so this is from actual Aceh fertility data and mortality data that's calculated. So that's the force of selection. That leads us to expect in the Hamilton theory an age pattern of mortality that looks like this. So here you see for humans, here you see the rapid increase after menopause. Now, so let me just comment on that. So first of all, there's this prediction of flat infant and child mortality up until age of reproductive maturity, which is obviously not the case empirically for humans or for most other species. And Hamilton was fully aware of that problem and wasn't sure what to do about it. And I should say also, I think this is an example of the under-imitation that we heard about earlier today, because many people, even people working in this area, think that Hamilton showed that it should be inversely proportional to Fisher's reproductive value, which would make it have a nice declining shape and so on, but it's not true. Now, if we include transfers in this story, then when an infant dies at birth, all of those resources that would have been devoted to it over the next 20 years are recaptured by the family or the kin group. There's very little wastage. Pregnancy isn't that expensive. When a 5-year-old dies, all the resources that had been invested in that 5-year-old up to that point are lost. When a 15-year-old dies or a 20-year-old dies, an enormous quantity of resources is lost. If you don't like putting it that way, that smells of sunk costs, which we know is a fallacy, you can recast that in terms of the expected net transfers that this individual will make over the rest of its life cycle, analogous to the expected net remaining fertility. And that's the way I'll try to refer to it now. Okay, so this gives a reason, a theory, for why mortality declines from birth until, say, sexual maturity. And I think it's a plausible story, but I think it's only a part of a much bigger story, and Levitas has a nice article along those lines. Adult mortality, well, I should have said more about this, but I think the idea is so familiar to everybody, I don't really need to. Adult mortality, post-reproductive years, continue to be used to promote own reproductive fitness, because grandparents or parents continue to support their own children through transfers, and perhaps grandchildren, and so on. We have the grandmother hypothesis, we have other stories, we have the role of the grandfather, we have insights from Kaplan and Girvin, and so on. So, in the 2003 paper, I developed a formal theory that integrated these two parts, and in that, I didn't know exactly how it was going to come out, but the way it came out is that the force of selection at each age was a weighted sum of the Hamilton effect, that is the share of remaining lifetime reproduction after that age, and then a new net transfer effect, which was equal to the share of future net transfers to be made remaining at that age. So it's a weighted average of those two. Now, for the transfer effect, it is 0 at birth, because over the remaining life cycle, first the birth is going to receive transfers, and then when adult, it's going to make transfers, and it's in the logic of the situation that those have to add up to 0 to satisfy a social budget constraint. So at birth, there's no force of selection from the transfer theory, but there is from the Hamilton part. Well, this is what the transfer part looks like. At birth, remaining net transfers over the life cycle are 0. Don't ask what these units are. And then as more and more transfers have been received and they're behind, then over the remainder of the life cycle, what remains begins to become more and more positive until the age of economic maturity is reached, when transfers are no longer received and start to be given. And then as someone moves through their lifetime of giving transfers, then the amount remaining to be given in the future declines, and we get this shape. And if we look at the shape of mortality age schedule implied by this, it's like this, and it's much more like, I don't remember where, I'll compare it in a moment to that Aceh life history. So what are the weights on fertility and on transfers? Well, in species that have no transfers, then the Hamilton weight, the Hamilton measure, remaining fertility, gets full weight, and the transfers get none. In a species, perhaps like humans, that has evolved to a point where the quantity-quality trade-off between number of offspring and quality of offspring has been optimized, then it turns out that the fertility effect drops out entirely because you have a few more kids, the quality goes down, it just compensates, and the transfer effect gets full weight. Possibly that's the human story. And most species would be somewhere in between. Okay, so here we have a comparison of the shapes, and the old Swedish life history is shown there, as well as the Hamilton story in the green line and so on, and it's a rather good fit. But as I note here, really it's a lot better than it should be, since this food-based story is surely only a small fraction of the whole thing that's going on, because we know there's protection, anyway, we don't need to go into all that. So, I've done other articles with Cyrus Chu and Chen, and there have been other work by Kaplan and Robson, and so on. And generally, at least in the work I've done on optimal life history modeling, a different approach, the results turn out to be very similar. There's, again, a kind of weighted average, weighted sum of the Hamilton and transfer effects, and you get the same sort of U-shaped prediction. But I'm not going to go into that now. I will mention that there are other topics here. Evolution of time preference is one. To what extent does an organism prefer to have a unit of energy today versus in a year or 10 years or tomorrow? Evolution of sexual dimorphism, evolution of menopause and adult division of labor, and possible upward transfers in a more recent paper with Chu and Lee, and then some two-sex modeling of optimal life histories with invasibility. But I'm not going to talk about that. I'm going to go in a different direction here. So, as I said before, the heavy and prolonged parental investment creates new threats to fitness. Parental death, early parental death, threatens the continued survival of offspring. And so there's a big payoff to having some sort of life insurance for parents or for the mother. That's the first threat. And the other is the life cycle squeeze, in which there's an increasing number of simultaneously dependent offspring for humans at a certain point in the reproductive life cycle. This was first pointed out, I think, by Shayanov, a Russian economist in the 1920s, and it's inefficient. And then demographic randomness makes this even worse. And so here is the Shayanov diagram from his book. And you see the ratio of consumers to producers peaks after about 13, 14, 15 years after marriage. And then it begins to decline as the kids get older and they begin to be productive themselves. We don't have units on the left-hand side here, but from other stuff in that work, I know it's about a doubling over those years. So Karen Kramer and I did a similar calculation for the Mayan data, And we have a peak at about 10 years. Very similar, really. And here you can see it's about 2.4. The dependency burden, you might say, is about 2.4 times as high 10 years into reproductive activities as it was at the start, before there were any kids. Okay, so this is an inefficient sort of demographic bottleneck on the ability to invest resources in kids, and it's a second kind of problem. So broader social sharing can resolve these problems because if food is shared within a broader group of relatives, perhaps including grandparents, maybe the father is sometimes there, father not, sometimes not, or perhaps including more distant kin, or perhaps some non-kin, then, for example, if a mother dies, then others may continue to provision and nurture the child. Of course, it's also possible that they will decide to kill the children, which also happens. And we here have a graphic account in Hill and Hurtado of such a debate and sort of struggle within the group about whether to keep or kill the orphans. So far as the life cycle squeeze goes, with a larger group of perhaps 8 to 25 individuals in a sharing group, much of the variation is smoothed out, provided there is food sharing within this group. And that avoids the bottleneck and promotes greater fitness. Well, I'm just saying there's some demographic benefits to this sort of broader cooperative breeding, social sharing, and so on. Of course, there are many other reasons why it might promote fitness, and I'm not going to be talking about them. I'm just focusing on this demographic aspect, which I think is not much noted. Now, social sharing solves some of these problems, as I just said, but it also changes the forces of selection on other aspects of the life history. So, in this case, it appears that parental survival, post-reproductive survival, is going to matter less if you have others who can step in to take your place. And so there may be less natural selection promoting post-reproductive survival in a social sharing arrangement like this. I'm assuming this persists for many thousands of years, not that it's just a transitory thing. An individual's high fertility is going to be less costly to siblings and to the mother in a group setting, because others are going to be bearing perhaps a big part of the costs or even some of the costs, and that's going to change the forces of selection. I would say this promotes a kind of evolutionary free riding, not necessarily behavioral free riding, but just it's going to affect our evolved mechanisms, birth interval lengths, and things like that. And it would be an inefficient distortion in the sense that if you were designing a life history for this group, it would involve lower fertility rather than higher fertility. For the individual, for the mother or the kin group, when an infant or a juvenile dies, the future transfers that would have been recaptured in a group that didn't have distant kin and non-kin in it, now won't be recaptured, because those came from sharing partners who were not closely related. And so that creates, just as there's a sort of natural selection incentive for evolved free riding in higher fertility, there's also an evolved incentive for natural selection to move towards lower than otherwise infant mortality and child mortality. I'm not talking about through the sharing, I'm talking about through the elimination of mutations that raise mortality at those ages and such things. This is another inefficient distortion. And there are other changes as well, including to the likelihood that there will be surviving offspring or offspring for a post-reproductive parent to help care for. So to investigate these themes and also the earlier themes, I developed a stochastic microsimulation model with Carl Bow and also with Tim Miller. This is written up in a 2008 article in PNAS. And I haven't seen this sort of thing elsewhere, but I may just have missed it. But in this model, each individual has a genome. The genome consists of the number of mutations affecting mortality at each age. The genome is inherited from, it's a unisex model. The genome is inherited by each birth, inherited from its mother, but there are 3 or 4 or 5 sort of randomly occurring mutations also. So this isn't clonal reproduction. And then these mutations are going to mean that the offspring have somewhat different mortality and other life history characteristics than the mother did. Then the offspring is raised in a kin group that may be embedded in a sharing group under different sharing rules or kin structure group rules. And food is produced by individuals according to their productive efficiency, which will depend on how much they consumed when they were young, how big and strong they grew when they were older, and it also depends on the density of the population in this defined area. And evolution then just takes place in this microsimulation as it goes forward. As I say here, we run it for 75,000 years. I'm not remembering how big these groups are, but in any event, these groups are big enough and the simulation is long enough so that these things always converge to the same configuration for the same given inputs. And I'll show a little bit of that in a moment. Okay, so if there's more food, more consumption in a group, which will happen partly if the age distribution is more favorable, there are more adults, more post-reproductive adults, fewer kids, whatever, then there will be higher fertility. Fertility goes up with food consumption, according to historical estimated data, and food consumption also reduces mortality. So that's the basic setup. There are more details in the PNAS story, but I want to show you some examples of how this turns out. So first of all, looking at the life insurance aspect, I'm showing the results here of 3 different specifications of the model. And the first one, a social group, consists of the oldest living female and her descendants for each sort of line of descent in this model. So M for matriarchal groups. Maybe a grandmother, maybe her daughter, maybe 2 daughters and their kids, something like that might occur. The K is a group of up to third cousins living together. And then the K, and in these cases, they're keeping all the food within the group. They're not sharing with other groups. But I think the most realistic is the K50-50. That's a group of 18 to 25, consisting of maybe 4 or 5 of these up to third cousin groups, and then each group is keeping half of its food within the kin group, that is maybe a group of 2 or 3 or 4 people, and then putting the other half of the food they forage in a common pool and sharing it with all others in this sharing group. Okay, so what happens? Well, in the matriarchal group, of course, if the mother dies, it's a disaster. So we have this high infant mortality here, almost 100%, well, infant and child mortality. And if the mother survives, infant and child mortality is low. That's in the matriarchal group. Once you have up to third cousins, you can see, surprisingly, that child mortality is higher. That's probably because of, well, I'm not sure exactly. I don't remember exactly why it's higher, but there's some perfectly plausible explanation, I'm sure. And if the mother is dead at the start of the interval, you can see there's a modest increase, but because there's food sharing and so on, others step in, so it's not a huge difference. And then in this group that includes non-kin and distant kin, both are very low, and that's for the reason I gave earlier, that selection now is going to sort of artificially or in a distorted way aim for lower fertility, select lower mortality than would otherwise occur because of the fact that a kin group loses all these socially provided resources in the event of the death of one of their kids. Okay. Now these are more general results for the shape of the life cycle mortality over the life cycle. So the first case is population-wide sharing. The whole population, I don't know, maybe 2,000 people, puts all that they produce in a common pool, and then people eat out of it according to their age and needs and so on. In that case, there's no selective pressure for post-reproductive survival, which it doesn't matter whether your mother survives or some other adult survives. And so you just get the Hamilton story, which is what we have here, with mortality rising early, towards the end of the reproductive period and after menopause. So that's as expected and as predicted. With matriarchal groups in which it's just close kin, you get this green line. Infant and child mortality are higher than in the Hamilton story because you recapture those resources if infant or child dies. And then you have extensive post-reproductive survival. With distant and non-kin, that's this yellow line, you have lower infant and child mortality than in the matriarchal case, as I was suggesting a moment ago, and you have even later post-reproductive increase in mortality. You have extensive post-reproductive survival. Okay. And I could go on about other social arrangements and how they turn out, but I think you get the idea. In some, we do reshuffling. 4 minutes. Okay. You have a different watch. Okay, so broader social sharing also creates new problems. So I've talked about the evolved free riding in fertility and in low mortality. I think this isn't part of the model, but it seems clear that there's going to be more muted selection for other traits like skill in hunting and so on, because your reproductive fitness doesn't depend so much on what you do. You're sharing with other people. If you're great, other people will benefit from your greatness. If you're lousy, you'll benefit from other people's being better and so on. And of course, you have to spend energy monitoring others to make sure they're sharing properly and doing their fair share. And there are other downsides. So I used the same simulation with Carl Bow to try to see which of these sort of kin arrangements, these social group arrangements, would have the highest reproductive fitness by putting them into direct competition with one another. In the sense they were each in their own silo in terms of the simulation model, except that the density, which determined how effective their foraging would be, was shared in general. They're all sharing the same foraging ground range. And so we can see which one will be able to prevail, which one can survive at the highest density. And of course, I thought that the broader sharing group was going to be most effective. Let me start with this. Yeah, so this is the actual first result in which what we're seeing is population size over time. and did 3 of each of these kinds of groups, and you can see they all came out exactly, or almost exactly the same. So the matriarchal group prevails. It's the smallest one, no life insurance, no life cycle squeeze smoothing or anything. And the compound group with the broadest sharing and the most complete insurance of all kinds goes down, goes extinct. And the up to third cousin is intermediate. Well, I spent a lot of time thinking about that, and Carl and I did pin down what the issue is, and it's interesting. It is because consumption in childhood boosts productivity in maturity. Now, depending on how sensitive that is, it may be that if you happen to be in a group in which you have no siblings or something like that, there's some randomness there, and you get better fed because you don't have competing siblings, and there are positive returns here, then you're going to grow up to be a kind of super adult, and then you're going to feed your kid better, your kids better, and they will become even more super adults, and so on. Then you end up with this kind of result, and because the matriarchal system has much more variance in outcomes. So the variance plus positive feedback to a good outcome can win. And if you take that feature out of the model, then you get the expected result, which is more resource driven. Well, I find this, I must be getting close to the end, and I find this interesting. I would encourage people to try something like this in terms of simulations with different kin structures and so on. Some of the ideas I've heard might be tested in these ways. Okay, so I'm going to leave that now, and the last thing I'm going to show is titled, "Perhaps Our Evolved Sociality Can Get Out of Hand When Paired with Large-Scale Politics and Institutions and Anonymous Transfer Systems that we have in modern societies, in which the public sector is making massive transfers, both to kids through public education and so on, and to older people through pensions, health care, long-term care, and so on and so forth." So this is the age profile of consumption by consumption in the United States in 1960. Older people were consuming less than younger adults. By 1981, after the introduction of publicly provided health care and Medicaid, which in the U.S., which provides for long-term care for people with few assets and so on, and Social Security became more generous, there begins to be an upward slope here, and by 2011 you can see, actually consumption by an 80-year-old relative to a 20-year-old, that has doubled. That ratio has doubled over the 50 years since 1960. So there's a huge change in the allocation of resources within the society. Hasn't favored children. It's been very much in favor of the elderly. You can't say from this that it's a bad thing or a good thing, but I suspect that it's sort of a runaway influence of institutions that change less slowly than the demography, and I think it's a bit of a problem in the United States. This isn't true in every rich industrial country, but it's true in Japan, Sweden, Germany, and a fair number of them. Anyway, I'm going to leave it at that. Thank you very much.
Thank you so much. We have 10 minutes for discussion.
Man. Hey, Ron.
Yeah.
Thanks so much. That was fantastic. So I wanted to ask you maybe a rather provocative question, whether or not we've been a bit misled by the metaphors of groups and pools, resource pooling, and if we might be better served by thinking about networks, and rather than thinking about a set of producers putting resources into a pool and a set of consumers drawing them out, but that there's producers and consumers, and there's maybe a plumbing system that connects producers and consumers, and that actually the fact that there's heterogeneous connections between individuals with different degrees of relatedness that we might actually be able to model these problems of, for example, moral hazard when it comes to work effort. We might be able to better model some of these inefficiencies that arise. What do you think about that?
Yeah, I think that's absolutely true. I was very struck by a presentation in the previous session by, I don't remember the first name, something like Adriana or something, Page, which was a network study of potentially of resources. Yes, so this is a blunt specification, and I can see many ways that I mean, a simulation, you can make the specification as fine-grained as you like. It's not like trying to do real empirical analysis. You use empirical analysis as an input. So these kinds of things, which in many contexts would be impossible, can be done here, and it would be interesting to see what their effects are. I agree.
Great talk, fantastic, fantastic. I was just wondering if the age of economic independence is different in hunter-gatherer societies and it's younger in the agricultural societies. How would that change the age-specific, like the selection pressure for age-specific mortality in these different places? And would you end up getting perhaps more diseases of onset in late adolescence in agricultural societies relative to hunter-gatherer societies?
Yeah, that's a very interesting point. I mean, at the time I was doing this, I just took it as a given that the processes of natural selection and evolution hadn't done anything very significant in the last 10 or 15,000 years. Now I've read things that suggest otherwise, and so it's a very interesting question about whether this could make, certainly in theory, what you say is exactly right, and it could happen. Whether in practice it would matter much, how flat the selection surface is in that area and so on, I'd have to look at to see. It should be, yeah, for humans, maybe it should be dominated by that economic maturity. Otherwise, some sort of average with the age of sexual maturity or onset of reproduction, which might be a little bit different. Yeah, thank you. Good idea.
Hi. Yeah. Yeah, well, I was going to actually. Ian Rickard, Durham University. Thank you very much. That's a really scary graph you've got up there at the end.
I was hoping I'd get that reaction.
Yeah, actually, could I just ask for a point of clarification? Because I wasn't quite sure about the main take-home point of the last set of simulations you were describing, and how, and particularly I'm trying to get my head around why the shape of the survival in early life was different between the kin sharing arrangements versus the broader sharing arrangements. Yeah, so if you could just say that again, that'd be really helpful. Thanks.
Yeah.
But the other thing was, in that simulation, do you have anything in there to take account of the sort of infancy as a discrete stage in which the child is completely dependent upon the mother as opposed to early childhood? Thanks.
These are done in 5-year age groups. So 0 to 4 is all lumped together. It could be separated out by single years of age, particularly now that computers are faster, and I don't think it would take prohibitively long. And I think it would be interesting, and I think in principle it should go back inside, in utero. This should apply from time of conception. You should have the highest failure rate then, to the extent that fetal mortality is really about failure and not about careful selection of viable fetuses. Yeah. But so what is the explanation? Well, you could say if an infant dies soon after birth, neonatal death, something like that, it's just not very costly. You've lost 9 months worth of, I think it's about 300 calories a day, is that right? Something like that is the energetic cost of pregnancy. And most of the cost of a child is in supporting it over the next 20 years. So that has a relatively low impact on the resource budget of this kin group. If the kid lives until 10 and something like 5 or 6 years of consumption have been invested in it as a transfer, then that 5 or 6 years of consumption is gone forever. And but what's in the future you recapture. What you're going to get between 5 and 20. I think I'm not focusing this answer very well. But now suppose you're in a broader sharing group. What you lose is your share of that, say, 5 years of consumption that went into producing a 10-year-old. Maybe that was only 1 or 2 years of consumption, and the other 3 or 4 years of consumption came from distant kin or non-kin. Okay, if that kid dies, you're going to get back the 1 or 2 years you put in, but you're not going to get back the 3 or 4 years. And so that creates this incentive, this sort of natural selection force to make mortality lower. Then.
Hi, I'm really fascinated by your last slide about this seemingly maladaptive upward transfer that not only societies but individuals as well, the level in the Western world, the level of individual upward transfer in old age exists is very interesting, and I wonder whether it seems like a new behavior, but it would be interesting to see. Because and I wanted to hear your thoughts about why you think this may have happened, because from a fitness maximizing perspective, the best thing an old person can do is to die, right?
Yeah.
And so,
well, okay.
From
So
an
let me say.
perspective.
So first of all, you have private transfers and you have public transfers. Private through the family. In every society I've ever seen, private transfers are downward, including Sweden, Japan, Germany, the U.S. today. Public transfers are mostly upward in rich industrial countries. In developing countries, public transfers are mostly downward for education, maybe child health. So what's happening is partly that population is getting older. So you keep the same per capita patterns, it's going to mean in aggregate, a greater share of GDP or something is going to go for population to older people. But that's not explaining this per capita curve. So what is explaining this per capita curve? If you look at agriculture, you see the beginning of something like this, perhaps because elderly now own property, they own the farm, something like that. That gives them a right, in some sense, to a share of the output generated by maybe their kids or other people who are working the farm. And so you see the beginning of this sort of retirement phase. And then, I don't know what the political process is that gets us started down the route of public provision for retirement benefits and broadly publicly provided health care. Probably the latter has very different roots than the former. I don't really have a very good explanation, but I think these programs are mostly introduced when they weren't a big deal. They weren't very expensive. But there's this institutional lag. They stay in place. It becomes politically extremely difficult to change them, and things get more expensive. There get to be more old people, and they turn into a sort of revenue pump for extracting income from people in the sort of working ages and transferring it to the elderly. Particularly, I would say, in the US and some countries. It seems to be much less true in some European countries.
Last questions. Yeah.
Hi, my name is Elliot Aguilar from the University of Pennsylvania. I was just curious if you thought about how these different sharing networks might correspond to people's behavior at different class levels, so that at lower class levels where resources are sparser, there may be wider sharing networks than further up the income ladder.
Well, I've thought about this really entirely in the hunter-gatherer and that evolutionary context rather than in the modern world, the contemporary world. This sort of thing, I have a big international project, and some part of that project, there are teams in lots of different countries, and in some of those countries this is being done by socioeconomic status, so you can see differences in private transfer flows and public transfer flows, taxes paid, benefits received, as well as sort of transfers received from others and given to others. You can see that by socioeconomic class, and there are interesting differences. But I think not in the spirit in which you're asking the question, which would require a different kind of data probably, and maybe a somewhat more ethnographic approach to data gathering than we use in this project.
Great, thank you so much.